Excellent. All right.
Yeah, that's a good way to put it. Delusional confidence. There's just a few parts where I was like, That was about it. That was the extent of my
That's what you thought?
Yeah, that's where they started.
All right. So we had finished up the first page. So this is a little bit about how we're going to determine what the strength of the association is. Right? We've talked about, that looks generally kind of weak or somewhat strong, or in the case of, which one was it? This one, I'm like, that's pretty strong. But how is it that this is actually calculated? So one of the things that they do to start off with is to ensure that the units don't matter. They start by normalizing the coordinates of every point. So they take a scatter plot like one of these, take every single ordered pair, and they find its z-score in terms of x and its z-score in terms of y. Finds those 2 points. Then once they've once they've standardized both the variables, then you're going to have a mean of 0, making the center of the scatter plot the origin. So they have recentered the scatter plot. This scatter plot would look somewhat the same if it was the original data. It just wouldn't be centered around 0, 0. It'd be centered some other place. You have the notes. They're the ones we did last week.
Left them at home.
I don't think I have any extras.
Sorry,
Oh my god.
I'm going out of town. Bring my backpack. All I probably
No, I said that 17 times.
It's only happened
Yeah, I'm
17
pretty
times.
sure that I don't.
Oh my goodness, Liam.
And we need to get this done, so...
I have regular paper. I can follow along.
Okay,
17.
thank you.
Yes, sir.
So what's going to happen is the way that we get R is we're going to take the sum of the product of those two z-scores for every point and then divide by n minus 1. Now this isn't something that you want to try and do by hand. It's awful. Okay? What this is R is the correlation coefficient. Sometimes just called the correlation. It gives us several things. It gives us the direction. If the correlation coefficient is positive, that means generally speaking, as we move from left to right, the data points will move further from the horizontal axis. And then vice versa. If we have a negative correlation coefficient, that doesn't mean it doesn't correlate strongly. It just means that as we move from right to left, the data points tend to move downwards. Okay, so you can think about it as just any other slope. If x is increasing causes y to increase, well, that's going to be a positive slope. If as x decreases, or should be increases, y decreases, well, that's going to be a negative slope. So, couple of words of warning. Before using correlation, we want to check the following conditions. First, it's got to be quantitative variables, and it has to be 2 of them. It's not just a single quantitative variable. So notice quantitative variables, plural. This is bivariate data. Secondly, it has to be fairly linear before you do this. You can get a correlation coefficient for something that's not very linear, but your results are going to be, well, not helpful. So we'll look at those in just a second, And then no outliers. If you have outliers, that tends to mess everything up. So for example, this one is okay to use to find the correlation coefficient on. This one, nope, not nearly straight enough. This one, nope, we've got this one outlier here. Now, by the way, this line, we'll talk more about it in the next chapter, but this is your line of best fit. Okay? This is a common AP question. Wow, that was a hint. That what would happen if I removed this point? What do you think would happen to the slope?
It would align more closely with the dots.
Yes, but what would happen to the slope of that line? It would decrease. And the other thing that would happen is because you don't have any points that are, like if I line these up, I'm like, man, those are all almost exactly on a line. Your correlation coefficient would increase in absolute value, right? In this case, it's positive, so it would go up. But if it was negative, it would go down. And then this one, it's like, okay, we got all kinds of problem going on here. As taken as a whole, is this data very linear? Right? Including all these points, is this very linear data? No, not very linear at all. Okay? So, nope, don't want to use correlation on that. So you should always check, can you get a correlation coefficient for any set of data? Absolutely. But if it's not straight or if it has outliers, it may not tell you anything worthwhile. All right, on to page 3, correlation properties. The sign of a correlation coefficient gives the direction of association. Now remember, association and correlation, I still have trouble, and I sometimes use correlation when I mean association. We'll talk about that in just a second. But the two are not the same. The correlation coefficient is a number, a single number. Okay? So if the correlation is positive, well, that means that my graph is generally going up from right to left. And if it's negative, it means my scatter plot is decreasing as I move from left to right. Sorry, I think I said right to left a second ago. Unless any of you read Hebrew, you probably don't do a lot of reading right to left. Correlation is always between -1 and 1, no matter what. Always, always, always. If the correlation is +1, that means that you have a perfectly straight set of data. It's never going to actually happen in practice. And a -1 would look like this, and a +1 would look like this. Okay? Now, it may or may not be at that high an angle. It could be at less of an angle. That's fine. But it's going to be, your data has to be perfectly straight to get a correlation of 1. So that's not going to happen. So an interesting point here is that correlation treats X and Y symmetrically. That is, the correlation of X with Y is the same as the correlation of Y with X. Those two are going to be the same. It doesn't make any difference. Sometimes that gets asked on AP questions. Well, they'll say something about the correlation of this with this is this, and then go, what's the correlation of opposite way? It's the same. The correlation is the same. Does not matter. Correlation has no units. If someone tells you that the correlation is something that has units on it, immediately reject that. Okay? Can't have units. Correlation is not affected by changes in the center or the scale of either variable. Now, that's a little bit different. So if you move your data set, to the right 15 and up 57, doesn't change the correlation. It doesn't change how closely it resembles a line. Also, if you change the scale and you spread it out more, it still isn't going to affect the correlation. That's a little bit counterintuitive, but it works. Okay, partly because the very first thing you're going to do is do a z-score. And when you spread it out, you get a larger standard deviation, which is what you're dividing by. And so the z-score isn't going to change. Notice correlation measures the strength of the linear association between the two variables. You can have something that has a strong association about something that looks like a parabola. The correlation on that's going to be really small, near zero, because it measures the strength of the linear association, not measures the strength of some association. And correlation is really sensitive to outliers. If you have an outlier, it tends to change your correlation by quite a lot. By the way, back to this one. Thank you. If we were to remove this point, the slope would decrease, but the correlation coefficient would increase because you don't have any that are a long way away from the line. All right, so some things to be careful of. The main one being this one. Correlation doesn't mean you're going to have causation. Just because your correlation is nearly 1 or nearly -1 doesn't mean that one thing caused another thing. Okay? So, I think I gave this example in class the other day. In elementary school, shoe size has a strong positive correlation with reading level. And it's like, does bigger feet cause you to read better? No. You want to look for other possible lurking variables. To explain the relationship. So, if you have a lurking variable, what happens is it looks like shoe size is causing reading level to increase. But what's actually happening is you have a lurking variable that causes both of those to increase. Okay? Yeah, age causes both of those to increase, generally speaking. Let's think about it in terms of health. So let's say that someone goes in and sees their doctor and they have an elevated blood pressure and they also have a faster than normal heart rate. Okay, a resting heart rate. And you're like, okay, and you do a study of some kind. We'll talk more about studies later. But you do a study and you find, hey, that happens a lot. That people who have an elevated heart rate also have higher blood pressure. And you're like, ooh, maybe this one causes that. Maybe you should look at the fact that, everyone who fits that in your study is 60 pounds overweight. Okay, that's the lurking variable that actually causes the other two. Okay, so and this is going to be important because there's another kind, we're not going to talk about it today, but there's another kind of, there's another variable called a confounding variable We'll talk about it later, but for right now, get lurking variables straight, because confounding causes people to lose their minds if you don't have lurking already set in your head. So a lurking variable is something that actually is causing the two variables that you think are related to each other. Okay, and there you can think of dozens of examples. Okay, you could go, in the fall of the year, I've noticed geese flying south, and I've noticed that the days get shorter. Are the geese somehow causing the Earth to rotate faster or something? Yeah. So you have to be, and the problem is there's a lot of ones that are obviously wrong, where the lurking variable is something else. The lurking variable there is that the time of the year it affects the day length and affects the geese's migratory patterns. Okay, but there are some that are more subtle. And that's partly why later on when we get into designing experiments, one of the things you want to do is try and prevent lurking variables, which is why you'll do things like you'll pick a random sample of people. If I was doing some health thing, and I only picked young, healthy people for my study, I might not find anything. I might find that something is actually age-related or any of a number of other things. So you want to get kind of a cross-section where it's like, it's not just old people, it's not just young people, it's not just healthy people, it's not just fat people, it's, you want to get a whole bunch of different people so that there isn't any lurking variable that's hiding in that set. Okay, so occasionally we will strengthen scatter plots, and I'm going to go back up to this one. There's no hope for straightening that out. Once you get it, curving that much where it's almost looking like a parabola, not real helpful. There was one in the book where it was more kind of like this, and it was definitely curved. Something like that, frequently if we take like the logarithm of one of the variables, we can straighten that out and make it more linear, which allows us to make predictions about things. Again, we'll get into how to make those predictions. So the last thing, keep association and correlation straight in your head. Association is a vague general term, right? Correlation is a precise measurement of the strength and direction of the linear relationship between two quantitative variables. Okay, so correlation coefficient is a number. Again, remember, it's unitless. If anyone tries to tell you it has units, then that's the wrong answer on a multiple choice. Any questions about this? Okay. I could have taken the time to print your. Sorry, I didn't realize we would.
I actually think this makes me remember it here.
Okay.
I'm actually